All right, so our last video for this week is about elementary matrices. And an elementary matrix is one row operation away from the identity matrix. So if you look down here in this example, like E1, if I were to just do 4 times row 1 plus row 3 back into row 3, I would end up getting that to 0 out there. Here, if I just switch row 1 and row 2, I'd be able to get this into the identity matrix. 1/5 E3, or row 3, I should say. Back into row 3, identity matrix. So an elementary matrix is just one row operation away from being the identity matrix. In this example, it does want us to compute all of these times A. I'm going to, in this video, just do the first one and kind of show you where we're going with this. So if I take EI times A, on my first and second rows, I'm going to end up getting the exact same thing. If you notice, turn by turn, if you go 1, 0, 0, A, 0, 0, I get A. Okay, if I multiply the next one, I just get B. If I multiply the next one, I just get C. Second one, I only get the middle. Now on this last one though, I'm going to get -4 times the top row plus the bottom row. And -4 times the top row plus the bottom row. Oop, that should be H. And -4 times the top row plus the bottom row. And notice that is essentially what we did here, right? If you were to take 4 times the top row and combine it with your bottom row, you're doing that row operation replacement. So if you notice here, it says if an elementary row operation is performed on an m by n matrix A, the resulting matrix can be written as an elementary matrix times A, where the m by m matrix E is created by performing the same row operation on IM. And what that means is, if you notice, this is our resulting matrix here. Well, this last row says take -4, multiply by the top, and add it down here. And that's the elementary matrix that I end up getting here. Okay. Each elementary matrix is invertible, and the inverse of E is the same type of transformation that takes E back to I, meaning E times its inverse is the same as its inverse times itself, and all of that gets you back to the identity matrix. So let's go ahead and find the inverse of EI. Well, I know that this is the row operation of 4 times 1 to get it back into the elementary form. So what that means is I can just say that the inverse is +4. Right there, because that's like the row operation that you would do to get this into the elementary matrix. Now let's go ahead and make sure that that's going to work. All right, so the first two are going to end up remaining the same. And let's think about what's going to happen in this spot specifically. So -4 times 1, 0 times 0, 4 times 4, I do end up getting 0 here. I end up getting 0 here, and then 1 here. Okay, so that has to be our inverse of E1. And you could check it the other way as well if you would like to. All right, so A is only going to be invertible, okay, if it is row, if and only if it is row equivalent to IN. And so if you have any type of elementary row operations that reduce A to IN, then we're going to end up finding out that that gives you your inverse matrix, excuse me. Now there is something that I did not copy over from the book as to the algorithm that you're going to use to do this. And what you're going to do is you're going to take A and augment it with I. And then you're going to do the sequence of elementary row operations that get A to be the identity matrix. And when you do that, you're going to end up getting the inverse on the right-hand side. That's what this theorem is essentially telling you, is A is invertible only if when you augment it, okay, essentially with I, and you do a series of row operations on A, that it then transforms this into I augmented with A inverse. All right, so let's do that here with this example. So we augment A. I don't know if augment is actually the right word here, but you place it next to the same n by n identity matrix here. All right, the first thing that we're going to do is switch these two rows. Okay, and then I am going to do -4 times row 1 plus row 3 and put that back into row 3. That gives me a 0 here. I end up getting -3 because of that 0. -12 plus 8 gives me -4. 0, 0. Oops. And let's do that again. -4 times row 1 plus 0 gives me -4. And then 1. All right, then I'm going to take 3 times row 2 plus row 3 and put that into row 3. That gives me a 0 here. 6 minus 4 gives me 2. 3 plus 0 gives me 3. -4, and then 1. All right, before I divide through, let's do negative row 3 plus row 2 and put that into row 2. So that's going to give me a 0 here. -2 here. 4 and -1. All right, well, now That makes it kind of tricky to multiply through here. So I'm just going to go ahead and divide that bottom row by 2 so that this is a 1. Divide by 2, divide by 2, divide by 2. Okay, so that leaves us as 3/2. This does change to -2. And then 1/2. Okay, so then -3 R3 plus row 1 back into row 1. And that should go ahead and zero out my top piece there. These are all going to stay. -2, -1, 3/2, -2, and 1/2. And the math isn't going to be super wonderful, but -3 times here, add 0, I'm going to get -9/2. 6 plus 1, I get 7. And then -3/2 right here. And so what that tells me is that this must be A inverse here.